So my name is Mike Reid, and I am one of the organizers for this symposium. I work for the Dunlap Institute for Astronomy and Astrophysics, where I coordinate public outreach and education sorts of things. And one of the things that we wanted to do for you today was for those of you who are teachers, or even those of you who have clubs, Royal Astronomical Society members, things like that, we wanted to talk a little bit about how you can take advantage of the transit to teach astronomy to young people. So I'm going to talk along with my collaborator, one of the graduate students in the Department of Astronomy, Mubdi Rahman, about talking about the transit with students. Now, I've sort of pitched my talk a little bit to high school students, but as you'll see, a lot of these activities that I'm going to talk about can be extended easily to people of other ages, okay? So astronomy tends to appear in the school curriculum in Ontario in grades 3, 6, 9, and 12. So you'll see us focusing on grades 6 and 9, and then Mubdi will talk about grade 12. So I would say that it's fairly accurate to characterize astronomy right now as going through something of a golden age. We have heard a lot about all these sort of misadventures in trying to figure out such simple things as the scale of the solar system. How big is the solar system, and how that took hundreds of years to figure out. But we are now at a stage in astronomy where we're starting to get pretty confident answers to some pretty big questions, okay? And nowadays, those of you who have had recent contact with the university know that it's getting very common for universities to offer big questions courses. So astronomy happens to be pretty uniquely poised to answer a lot of the big questions that people are interested in asking. So these are the kinds of questions we get a lot from students. How did the solar system form? We actually know that pretty well right now, which is very interesting, very impressive, I would say. How did the Earth itself form? We have a reasonably good handle on that, although still some work to do. But there are some big questions here that we really don't have much to say about. Now, my biology colleagues might disagree with me on these points, but I would say we don't really know how life formed, and we certainly don't know at all whether life exists elsewhere in the universe. These are big questions that people get asked over and over again. You've actually heard these themes alluded to several times already today, with people talking about observing a transit of Venus to try and determine whether Venus has an atmosphere so that they can try and work out whether it's got life, okay? These questions are only going to be answered, these big questions, by actually finding other planets, probably planets outside our solar system, which are capable of supporting life. We don't think at this point that any of the planets in our solar system are likely to support life that's of a similar type to that we find on the Earth. So the Holy Grail, or one of the few Holy Grails in astronomy right now, is to find an Earth-like planet somewhere else in the universe. And as you'll see, this is deeply connected with the topic of the transit of Venus. So you've already heard a little bit from Jay about using a transit to find a planet orbiting another star. And the basic idea, of course, is that, here's a transit of Venus. You can detect the dimming of the star as the planet passes in front of it, and thereby indirectly deduce the presence of that planet, and usually work out something about the planet, its size, its mass, perhaps its temperature, things like that. Now, students, we find, are very motivated by novelty. They don't really want to hear all that much about things we've known for hundreds of years. They want to hear about things that are new, right? And so I would say that the transit of Venus, even though it's something that has a lot of historical connections to it, because it's a once-in-a-lifetime sort of thing, at least for the majority of these students, barring major advances in medicine, probably most of them will not see the next transit. We can hope. So this is just a great opportunity. The fact that it's something that happens rarely is itself a really great thing for getting students interested in it. In the astronomy curriculum in Ontario, there are a number of goals which are actually, they're sort of stated in different ways for different grades, but they're pretty common to most grades, all the way from grade 3 to grade 12. We really want students to understand the scientific method. What we don't want is for students to think that science is revealed to astronomers by some mysterious process. We chisel it into tablets and then photocopy those into textbooks, right? Which is how a lot of them think science works, that somehow we have direct connection to God and we just sort of inherit the knowledge. We want them to make observations, in part so that they understand what the scientific method is. Transit of Venus is a perfect opportunity for them to do this. It's a new, novel thing that they can go and observe themselves. And then there's some sort of lesser goals here, sort of generally become familiar with the solar system, be able to simulate celestial phenomena, and explain the causes of things. Again, getting back to that scientific method. So we can use the transit of Venus to do all of these things. Now, you've already heard that historically speaking, transits of Venus were mainly used to measure the distance to the sun. And there are the many misadventures. That's a great thing to talk to students about. They really like the story of Guillaume Le Gentil losing his fortune and his wife and everything else. So they were used historically to measure the distance to the sun. And for more advanced students, you can actually go through the math of how to do that. It's just a little bit of, well, actually it can be quite a lot of trigonometry. So not great for younger students. And actually Mubdi will tell you a little bit more about how you would go through that with older students. So I'll let him talk about that. But today, the emphasis that we put on transits of Venus isn't so much the historical uses of the transits to determine the distance to the sun, but we try and cast them in the light of tools for finding exoplanets. And this is a really, really great opportunity, as I say, to get students interested in making measurements that help us find exoplanets. Some of you may know that one of the first measurements using the transit method of finding an exoplanet was actually done using a small telescope, an amateur grade kind of telescope in a parking lot. This is not science that's actually beyond young people. They can do this with a small amount of help, depending on their age, or even with no help if they're a little older students. So you're going to hear more about this from James Graham in a little bit, who's getting quite good at finding planets using various methods, including transits, but also actually directly taking pictures of them. But the basic idea, I think, is familiar to most people by now. Again, you know that we've already found many other planetary systems just by waiting for their planets to pass in front of their stars. You get a transit, you measure the dimming of the star. So actually, I'll skip that since other people have talked about it. I want to talk a little bit about what you can do on June 5th and in the lead up to June 5th to get young people interested in the transit. So what will you actually see if you go out? Well, one thing I want to actually, I'll start passing these around. One of the nice things about, everyone can take a pair of these and pass them along. One of the nice things about a transit of Venus is that you can actually see it with the unaided eye, assuming you have reasonably good vision. And when I say unaided, I mean, you don't need a telescope. You do, however, need a pair of those glasses. Do not stare at the sun, right? So this is an important thing to emphasize to young people. So we at the Dunlap Institute have printed up almost 50,000 pairs of these glasses that have been distributed across the country, and we'll be handing out a whole lot of them here in Toronto closer to the time of the event. I'm giving everyone here a pair. If you don't get one as they pass around, come up at the end and I'll give you another pair. And we hope to get a lot of people to actually go out and look at the transit on June 5th. So for those of you who haven't done this before, a little unsure what to expect, basically at about, you could start watching maybe a little bit before 6. The transit itself will start in Toronto just about at 6, a couple of minutes after. So at 5:30, you won't see anything with the transit glasses. Just after 6, you get your first contact. Venus will actually touch the sun, and you can look for that black drop effect. And then in Toronto, depending on, or at least in this general part of the world, depending on exactly where you are, you can see the transit until about 9 o'clock when the sun sets. Okay? Obviously, if you're in downtown Toronto, there might be buildings in your way, and it might be a little bit more difficult. So one of our goals is to make that easier. And what we're doing this year, as hopefully a service that all of you will enjoy and make use of, is we have Varsity Stadium just down the street. And a very nice thing about Varsity Stadium here on U of T campus is that all the bleachers face the transit. It's like they designed it that way. So we will be welcoming everyone to come to the University of Toronto and join us in Varsity Stadium, where we will have a whole pile of things going on. We'll have a bunch of telescopes set up, including a special solar telescope that's got a good H-alpha filter on it, so you can not only see the transit, you can also see sunspots, you can see flares and things like that. And we'll have piles of astronomers there wearing these Ask Me, I'm an Astronomer buttons, so that you can approach them and bring your kids, let them ask questions about astronomy. So that's a great thing. There'll be more about that on our website, universe.utoronto.ca, in the coming week or so. At this event, we're going to be replicating one of these sorts of types of measurements that people have talked about already. observing the transit from many different points around the world. It used to be you had to get on a boat and travel for 3 or 4 months. Maybe you're Captain Cook. You have to go halfway around the planet. Now it's very easy. Everyone streams this live to the internet. We all go to Varsity Stadium and we put their observations on the Jumbotron. And we can go click, 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 India, Australia, Japan, cycle through, and you can see the transit from all over the world. So that's a great way to illustrate to students what exactly is going on during the transit, okay? And they can, if they like, make some measurements there using the streams from other locations. Because we're very interested in getting as many people as possible interested in the transit, we have published this informative brochure that describes what's going on. It's available on our website in 9 languages and is being distributed to community centers where people generally speak those languages around the Greater Toronto area. Now, that's the event that we'll be doing on the day of the transit here on campus. But there are lots of things that people can do to prepare themselves to get ready for the transit. One of those is to just simulate the transit. So there are lots of ways you can do this. Now, with teachers in mind, I know teachers have budgets of effectively $0 and have to repurpose things that have already been used for other purposes. So we've done this experiment. This is a great thing you can do with kids. You get a big ball and a little ball. Ideally, they're sort of scaled roughly right so that your big ball is about as big compared to the small ball as the sun is to Venus. So beach ball and a ball bearing works reasonably well. But kids don't notice these things too much, so you don't have to worry terribly much, okay? And you can get kids to simulate a transit. We actually do these in university classes, right? You actually get them to bodily get up, and someone holds a beach ball and they are the sun. Someone has the little ball, they are Venus. And they sort of animate out a transit for themselves and figure out what it is. There's a slightly more sophisticated version of this you can do. This is a transit simulator that was built by a group of people, one of whom is now a postdoctoral fellow here at the Canadian Institute for Theoretical Astrophysics, Linda Strubba. And this is perfectly designed for teachers because it costs almost nothing to build, but works really well. So this is a little transit simulator. Basically, it's a kind of a lazy Susan with a light bulb on it. It's got an arm and a styrofoam ball to represent the planet. Okay, seems kind of ho-hum to you. You think, oh, you put something on a turntable, it's not that exciting, right? Kids go crazy for this. We've built 4 of these and we take them around to schools. They love this. We took this to a grade 9 class recently in Scarborough, and what we wanted them to do was to use a light meter, move the artificial planet around the light bulb, and measure the light curve, measure the dimming of the star as the planet transits. The kids went crazy. They started pulling out their phones and changing the color of the screen on their phone to simulate what if there was a red giant next to the star. And they started tilting it and using a paper clip to put little fake rings on the planet and things like that. They go crazy, and they can figure out how all of these things would affect the light curve. And this helps them understand exactly the measurements that astronomers do to deduce the presence of exoplanets in other solar systems. The instructions for building one of these are at universe.utoronto.ca/transit2012. They cost about $40. That's for the first one. If you build several at a time, they cost much less because you buy multiple parts all in a pack. And they're really fun for students. They like those. We have worksheets designed for people who want to build one of these things to use with the transit simulator or without the transit simulator. These worksheets are all available on the same website, universe.utoronto.ca, and they help students use the device to actually make their own light curve. You can pair one of those devices with an actual light meter, the same sort of light meter that photographers use. That's a little bit more pricey. It can cost maybe $70 to get a decent light meter, but the students, again, they really like it, and it's a good experience for them. Another route you can go is to use, again, keeping the sort of low-cost thing in mind, you can use Stellarium, which is a piece of software maybe some of you are familiar with. It's a sky simulator piece of software that students can use to actually simulate the transit on their own, and it's free. It's available on the web. Again, students tend to really like that. I use that all the time in my classes. Actually observing the transit, though, is the gold standard. Simulating is great because if you're actually teaching a school classroom, you can't actually go out and observe the transit. It occurs after school hours. So you can simulate it with the students and then encourage them to go out and observe it, or even organize an evening event. So there's a number of ways to do that, and there are loads of them described on the Exploratorium has a great website that shows you all the different kinds of cameras you can build with students of different ability levels and ages. Really simply, you can build a pinhole camera. Right? Take a piece of cardboard, put a piece of, you cut a hole in it, put a piece of aluminum foil in the hole, and poke a very, very tiny hole in the aluminum foil, and you can use that to project an image of the sun. Very, very simple. You could also buy, if you don't feel even that technologically inclined to poke holes in tinfoil, which admittedly some people have trouble with, you can buy one of these things pre-made. It's a slightly more sophisticated version of it, where basically it's a pinhole camera. You point this end at the sun. It focuses the light onto a mirror, which shines the image back up onto the inside of this cardboard dome, and you get a very nice, this is a picture of the 2004 transit. So you can do really nice transit observations with one of those solar scopes. As Jay mentioned, there is an app for this. My God, do students like apps. Even if you don't tell them about the app, they will find it. So this is the Great Transit of Venus app. I guarantee they will pull the phone out at some point. So this is exactly what Jay said. It's an app you can download for Android, iPhone, whatever else. And the students can go out and they can do the measurement en masse. This can help them understand things like error analysis in science. They understand why multiple people need to make the same measurement, and then you average the results together. So this app allows them to each take measurements of when they have first contact, second contact, and so on, and then average their results together to measure the distance to the sun. There are a number of sort of student-friendly transit events going on. There's, of course, the one that I mentioned to you on June 5th here at U of T. In 2 weeks from today, we will have Science Rendezvous, which will cover a good chunk of this campus, mainly over on St. George Street, and the Toronto Reference Library, where we'll be handing out more of those glasses, having lots of astronomers available with transit simulators to go through the whole idea of a transit with kids. And then our event in Varsity Stadium, which I invite all of you to come and join us at. So those are some ideas for ways to talk about the transit with kids. These are mainly for high school kids, although some of those ideas also work well for younger children. But to maybe let you get into a little bit more of the nitty-gritty details, I will turn it over to my colleague, Mubdi Rahman, who is mere weeks away from becoming Dr. Mubdi Rahman. And let me just show you his presentation here.
All right, thanks, Mike. So in this section of this talk, I'll be focusing on specifically looking at how we can use transits in the grade 11/12 physics curriculum. And there are slight differences between using the transit as an educational tool for the grade 6 or grade 9 science curriculum, where basically every student has to take it, versus something like the grade 11 or 12, where it's a much more pragmatic course. These are students that have to take it because they want to go into a science program in university. So they're taking it for the purpose of learning physics as opposed to something that they need to take and can be used to inspire. So rather than the incentive being what's cool and new, the incentive for this can be taking a simple measurement and figuring out that with the math that they know at a high school level, they can figure out a very big question. How far is the sun really? Just with the simple calculations that they can do through the measurement of the transit of Venus. And I'll go over this very briefly. It's a very simplified version of this, so I know some people are probably going to pounce on me for the simplifications I made. But with this very simple example, they can get the distance between the sun to the Earth to within about 50%, using just the high school math they do. And they can actually do a little better. They can get to within 10% if they take into account some of the more specific details that they have the math to be able to do. So what are the two main concepts that they need? They need to understand Kepler's laws, or they need to know of Kepler's laws, specifically the idea of the relationship between the semi-major axis, or the distance between a planet and the sun, and its relationship to its period, or how long it takes to orbit the sun. And they need to understand parallax. The joy of these are that they're both very, very simple concepts. And that means that the problem is primarily geometric. You don't need calculus. You don't need any advanced mathematics to actually do this. You do need to dabble in a bit of geometry, which we simplified for them. But it's completely solvable. I don't know why you'd want to solve it, because classical geometry can be really annoying, but it is solvable. So how do you set this problem up for the students? Well, the simple idea of the transit of Venus is that you're looking at Venus crossing the sun at two different locations on the Earth, or multiple different locations on the Earth, where you have a baseline, where you have a distance between the two places. Now, to simplify the math for the students, we've chosen two places, Shanghai and Port Macquarie in Australia, because they're both roughly the same distance from the equator. If you don't do that, then there's additional math that they need to take into account for the rotation of the Earth itself. So we just simplified it for them. And we can measure the distance. Heck, the Greeks knew how to measure the distance. We can measure the distance between those two. So we give them 6,600 kilometers, and we give them an angle of 62 degrees. So this is our simulated transit, not quite as nice and sexy as the pictures you've been seeing up until now, but giving you a start time, middle time, and end time for the transit of Venus from Shanghai. Now, dramatically different is a transit of Venus from Port McCary, where once again you have the start time, the middle time, and the end time. Now, if you notice, the difference is about 5 minutes. So over the course of something like 6 hours, it's a 5-minute change. So the question is, can you use that time, or the change in time, to determine what the difference in the angle is? Because essentially what you're trying to look for is the angle between you, Venus, and the sun. And there's this wonderful geometric identity that can be solved, and it's based on determining how long a chord is across the sun, something that I completely did not remember from my grade 10 or 11 classical geometry. And it's frankly not particularly important to the concept of this experiment. So you can give to them the geometric identity. You can just tell them that this is how long, or what the angle is given a certain time. And it's a ratio of the total time to the difference in time times this geometric factor times the size of the sun that gives you the angle. So now that you know the angular difference, the next thing you need to go through is Kepler's laws, which is something that they do cover in the grade 12 physics curricula. And the idea is that you know the ratio between the distance between Venus and the sun and the Earth and the sun. So you can tell how far apart, in terms of that length, Venus is away from the Earth at the point of transit. And once again, we simplify it, calling them roughly circular orbits. And this is the tricky part. It's a similar triangle problem. At the end of the day, all it comes down to is what is this angle here, which you've measured based on the difference in transit times, and you've measured the distance between Port McCary and Shanghai, or the other way around. And based on that, you can tell what that distance is going to be. Just a simple similar triangles issue. And from that relationship alone, from these 4 steps, you can get the distance between the sun and the Earth to within approximately 50%. So where are the complications? Well, the complications are the sun is also reasonably close. So the sun is going to appear to move as well. It's going to appear to have a parallax. And if you take that into account as well, you can get the measurement in something, once again, completely within the grade 11 and 12 physics scope. You can get the measurement of, or the calculation of how far the sun is from the Earth to within 10%. So where does this fall in the curriculum? So in the grade 11 and 12 curriculum, they both have this entire idea of synthesizing, analyzing, and interpreting qualitative and quantitative data. So solving problems using this data. Now, all the math they have covered by grade 10 or grade 11 at this point. The only thing that might be a little tricky is the trigonometry. At the grade 11 level, you're covering the entire idea of solving problems involving distance, positions, and displacements. So there's something a little more advanced, or for the more advanced grade 11 level. For the grade 12 level, you're talking about solving problems involving motion, specifically circular motion. So this is directly in the curricula, and so easily can be swapped in as an exercise in this case. And falling in with Kepler's laws, you want to analyze, solve problems, and relate to Newton's law of universal gravitation, circular motion. So they have to do orbits anyway. So this gives them a powerful example of what Newton's laws and what Kepler's laws can do for them in terms of solving a very, very basic question. And on that note, I think we take questions.
I think we don't have time.
Oh, we don't have questions? All right.
We're going to go on to the next.